All right, folks, it's Bass Action, back in action here. In this video, we're going to go through a couple formulas. We're going to start looking at degrees, minutes, and seconds. That's going to give us a more accurate way of representing our degrees. We're going to look at arc length in terms of angles measured in radians, and then we're going to look at area of a sector also in terms of angles measured in radians. So we're going to start up here at the top with our degrees, minutes, and seconds, and we're going to just fill in a couple conversions before we get into our formulas. So the first thing we're going to look at is that 1 revolution is going to be 360 degrees. 1 degree will be 60 minutes. We're also going to be able to represent that 60 minutes with a 60 and then a little tick mark here. It'll look like 60 feet, but we understand that it'll mean minutes. And then where our 1 minute is going to equal 60 seconds. And that notation would be 60 and it'll look like inches, but again, we're going to understand that this means seconds. So on our first example here, we want to convert 70 degrees, 12 minutes, and 36 seconds to a decimal that's in terms of degrees. Now, since we're going to degrees, we're going to just keep this 70 degrees here. So this is just going to be kept just as it is. Then we're going to go ahead and we're going to take our 12 minutes and we're going to convert it to degrees. And we've got a nice conversion right here for that. So in order to do that, certainly you could do this probably in your head, but if we want to write this out in a more formal setting, it would look like 12 minutes. I'd say 12 minutes over 1. And then I know that 60 minutes, since I want those minutes to cancel, 60 minutes will equal 1 degree. And that's going to allow me to get to my value, converting my minutes to degrees. Now, this one actually would reduce quite nicely. 12 is going to go into 65 times, and 1 over 5 would be equal to a 0.2. Now, most of the time, you're probably going to want to bust out a calculator for these, but sometimes we'll give you some nice numbers like this. Now, in the next one, we want to take our seconds to degrees, and you'll notice that the conversion that I gave you over here only takes you from minutes to seconds, and so it's only going to let us move back and forth there. So we're going to throw in another conversion, and that one would be 1 degree is going to be equal to 3,600 seconds. So that is going to allow us to go directly from seconds to degrees. So again, we're going to take our 36 seconds. I'm going to put that over 1. Then I know that 3,600 seconds is equal to 1 degree. And again, I gave you kind of some numbers that are going to be nice here. So our 36 and our 3,600, this is certainly going to become a 100 down there. So our 1 over our 100, we could write that as a decimal without using a calculator, which would be 0.01. And then we're just going to add all of these values together, our 70 degrees, our 0.2, our 0.01, and that will get us a final answer of 70.21 degrees. Now, most of the time, you're probably going to need a calculator for these, especially if the numbers didn't work out quite so nicely. Over here, we're going to go the other direction. We have this decimal, and we want to break it down into its pieces. So just like before, we're going to keep this whole number because that's going to be our total number of our whole amount of degrees. Then we're going to take just this decimal portion, the 0.628, and we're going to convert that. We're going to go from our degrees to our minutes using our conversions. So that's going to allow us to take our 0.628, and now we can just multiply this by 60, and that's going to give us a whole number and a decimal, and that's going to give us 37.68. So what we'll do is we'll keep this portion right here, and that will become our minutes. We'll take this remaining decimal. We don't round yet. This remaining decimal is going to allow us to go from minutes to seconds because now we've converted it to minutes. So we'll take our 0.68, and now we can multiply by 60 again using the conversions from right above, and that's going to give us 40.8 seconds. And now we can go ahead and round that one. We won't round until the end, and we will round this to 41 seconds. So when we look at our final answer, we can see that we'll have 38 degrees, we'll have 37 minutes, and 41 seconds. So that's going to be our final answer right there. Now the next thing that we're going to take a look at we're going to convert our formula that we've been working with from geometry into something that'll be useful for us when we're given angles in radians. What I want to really emphasize here is that this formula up here at the top, some of you might have been working with this in a proportion format, but it's the same idea. Arc length is going to be the circumference of the circle times whatever portion of the circle you want. If you are given a measure, an arc, a central angle measure in degrees, this is definitely still going to be your easier formula. If you're given a formula or an angle that's in radians or asked for radians, we're going to convert it to this new formula. So I want you to understand how this is working. So we've got our circumference and our arc measure over 360. In this first step, all I did was I took my circumference, just the word circumference, and I replaced it with the formula. And of course, the arc measure portion, you can see that this part still stayed the same. So that got me to here. The next thing that I did, all that I did was I just reduced. My 2 went into 360, and that got me to my next step of 180. So from here to here, that was all I did. Then I did a little bit of rearranging, okay? So looking at this pi times r in the 180, I just grouped that a little differently. I pulled out the r separately, and then the pi over 180 went right here. Now, from here, what we did was this pi over 180 times the arc measure. Remember, the arc measure is the measure of the central angle. This is actually simply our measurement for an angle in radians. So this is going to be our measure of our angle in radians. And then the r is still just going to be the radius of the circle. So if you are asked to find the length of an arc and you're given radians or it wants an answer in radians, then you are going to use this new formula. Our S, this capital S, is still just going to now represent arc length. But this is going to allow us to work with radians instead of having to maybe convert back and forth over and over again. So let's look at a quick example. If the radius of a circle, so now we know our radius, so the radius of a circle is 12 inches, and it's giving us the central angle in radians, we can now find the length of the arc without converting this angle all the way back to degrees. All that we would have to do here is use our new formula, S equals R theta. So S, we're going to take our radius of 12. I'm going to put it over 1. I'm going to take my 7 pi over 10. And of course, I can do a little bit of reducing here. My 12 and my 10 are going to reduce to a nice 6 and 5. And then I can multiply straight across, and that's going to give me 42 pi over 5. And of course, the arc length should be a nice distance around, so that in this case is going to be inches. So notice this is a lot faster than trying to convert this angle all the way to degrees and then apply the geometry formula. We're going to do a similar process with the area of a sector. Remember, the area of a sector is going to be a shaded region here. So we're going to do the same thing. Area of our sector is still going to be a portion of the circle, but now it's times the area. So same idea, we took area and just replaced it with its formula of pi r squared. Then I did, again, a little bit of rearranging. So I took my 360 and I split that apart. That's where this 2 and the 180 came from. And I split that apart so that I can now, again, identify the representation of the arc in radians. Okay, so that arc measure in radians. So it's our pi over 1. This is a degrees over 180. This gets us our theta value over here, specifically in radians. And then we're just going to grab all the other parts, the 1/2 that I then had to pull out, and the r squared from the area formula. So now, this problem, you can see, we're going to try to work backwards. We're going to actually find the radius of our circle. So this time, I have the measure of a central angle, and it's in radians, and I don't want to have to convert it. And I'm told that the area of my circle is 4 pi centimeters squared. So I'm going to now use this new formula. If you want, you can give yourself a reminder that the r here is going to be the radius. Okay, and that's what we're solving for. So now what we're going to do is we're just going to substitute that in. We're going to say 4 pi, that's what we know the sector is. We're going to fill in our 1/2. We're going to go ahead and fill in our r squared because we don't know what it is. And then we're going to fill in the measure of our angle in radians, 2 pi over 9. Now we can start doing a little cleaning up. Those 2's, of course, cancel. We can see on opposite sides of this equation that those pi's are going to cancel. And then I can go ahead and I can multiply both sides by 9. And I'm going to then have 36 equals r squared. So the radius of my circle is going to be 6 centimeters. And again, so much easier than trying to convert this angle back to degrees and then applying an old formula. We just substitute in to our new formula. So the goal here is for you to become comfortable with both formulas, the new formulas and the old, so you can work with whatever form you're given.